Good evening, everyone. Welcome to the Centenary Celebration of the Department of Mechanical Engineering, IIEST Shibpur. Today, we are here for the Fourth Centenary Lecture under the Centenary Lecture series. We have Professor Kamal Sarkar with us today to give a lecture on the topic A Tourist's Guide Through the Nano World. The session would be chaired by our honorable alumnus, Dr. Biman Ghosh, past president of Gabesu and currently manager at Rockwell Automation. Sir, please take over the session.
Good evening. Very good morning to Kamal, very early morning actually for him, and good afternoon for people in the other part of the world. I deem it a great pleasure to introduce Professor Kamal Sarkar to this August gathering. And Kamal is actually, in our B college term, we always address our dadas, no matter what is my year of graduation, I call him Kamal. Kamal started his career with Indian Space Research Organization in 1969. And, he actually witnessed the entire growth of our Indian Space Research Organization because that's the early 70s time when we are growing. And while serving Indian Space Research Organization, he actually decided to pursue his career or enhance his career in the area of material science as well and joined Indian Institute of Technology, Kanpur, where Professor Amitabh Ghosh served a long tenure. And Kamala did his master's with Professor P.N. Murthy. And that's the time the Advanced Center for Material Science was actually evolving in IIT Kanpur. And Kamala graduated with his MTech from IIT Kanpur while still continuing to serve Indian Space Research Organization. And then in 1976, he decided to come to US to pursue his graduate schooling with University of Tennessee System, and finally graduated from UT Knoxville. And while doing his PhD, he actually worked in the Space Institute for UT Knoxville, where there are specific focus on many different areas, including remote sensing. And this is actually the time when Kamala expanded his... Please unmute yourself if you are not talking. And he actually learned the skills how to use finite element method in determining Young's modulus for glass fiber composites. And then finally, he continued to understand the behavior of polymer matrix composites using this finite element method. Commonly, as we all know, after his graduation, he joined industry. Although he just said a few minutes back that
Sir, you have been muted.
Yeah, I have unmuted myself. So Kamala joined industries and served many different industries, especially in the medical devices company in Minneapolis, in San Diego. And finally, he came back to academics in 2006. One of the key areas of Kamala's career is utilizing the artificial intelligence methodologies in detecting the objects for blind people. This is something actually he secured a National Science Foundation grant in US, and he collaborated in many different countries, including developing countries like Brazil, to find out the low-cost solution to create a very good social impact. And this is simple methodology he might illustrate later, but how you can sense the object and essentially convert the imagery information of the object to the person who wants to feel the object, touch the object, and essentially learn about the object. And this is a very strong, impactful research, I think, for the people who doesn't have the vision to see other things like we do see. Kamal is passionate about community development work. He actually pioneered the formation of our Bengali association in Trivandrum, now Thiruvananthapuram. He established the Bengali library over there. He was very active in the Indian community. And when he was in New Jersey, which is called the Garden State in the United States, he actually established the Indian Community Center in New Jersey. but he left New Jersey for Minneapolis and other things. So that will be his career journey. But again, it is my great pleasure to introduce Professor Kamal Sarkar to talk about a tourist guide to the nano world. Kamal, please.
Thank you, Biman. This is exactly happens when a brother introduces the Dada. He goes over the top and he basically smears fact and fiction. I am nowhere near what he said. I am just one thing I can tell you. I am a BE college alumni. I am very happy to go back to BE college, come back to BE college after 60 years, when many of the present students' dads were not even born. I was I am like actually a dinosaur. I was roaming in the halls and backways and classes and hostels in those days. So coming back to from dinosaur age to I'll be talking about the nano world, basically mixing up something like facts and fiction together. This is a really exciting journey. Before I go further, let me tell you one thing. I'm really honored to be here. Particularly, I'm seeing the people like Amitabha Uchudda. This is the luminaries of our university, of our institute. I'm very, very happy. Even I'm a little scared to, frankly, to open my mouth in front of them because I do know if I make one mistake, they'll, what's going on? So please take with a pinch of salt whatever I say. Another quick comment I'm to make regarding my presentation is that I want to make it interactive so that you can jump in anytime. If you have any question, you can ask me. And all my slides are numbered so that you can jot down the number and say, Kamalda, can we ask this thing, that thing? Okay, I'll be more than happy. Another point I want to make, please, for heaven's sake, don't call me sir. You can call me Dada, you can call me Jetu, you can call me Dadu, I don't mind. But don't call me sir. Okay, I don't deserve it. Okay, I'm a very simple person. Okay. Third thing is that I'm really happy to make my interest level exposed to all the luminaries of this August assembly. I'm really excited about it. All I have to do one thing, and if I do it, I'll be very happy. I'm to share my excitement. I want you, anybody, particularly I'm focusing my presentation to the students, not to the other people or junior faculty or faculty member, to get interested into the area of nano. It's a really very exciting word, very exciting word. With this, I'm going to start my presentation. This is not the right one. Let me go back. Give me a second, please. Sorry. And what I'm going to talk about is, it is an interesting point to make that I started my career in space research, big numbers. Now I'm going to talk about very, very, very small numbers. That is, we are talking about nano world. And what I'm going to see is, come on. Give me a second. 22. So, okay, I got it. Can I see it now?
It's loading, but not there yet.
Not there yet? Is it still there or no? It's still loading.
No, it's not there.
What happened? Why it is
Are
not
you
there?
presenting with two monitors, Kamal?
Yeah.
Do you have two
Oh
monitors?
yeah. Can we?
Yeah,
No,
yeah,
no,
yeah,
I've
yeah.
got one.
This is it. This is it.
Okay.
You go
Sorry
to
for
slideshow mode and yeah.
Okay. Sorry for the hiccup. Okay.
Very good. We are all good here. Thank you.
Okay. Thank you. So my presentation, I call it a tourist guide to the nano world. As I told you, it is mostly focused for the students. Now, this is the way my journey will start. I'll first welcome you all to Nano World. We'll talk about what is nano. And question is that what's the big deal about nano? Then I'll talk about the lots of fun going around the world. How to jump into the game. How can we start doing research in nanomaterial? Then we'll talk about two most research area in nanomanufacturing, electrospinning to force spinning. And then we'll talk about another methodology to get into nano, from waste glass to nano glasses. Then we'll give you some warning sign, what to do, what not to do, and then summarize what we talked about. As I told you, it's always interactive. You can, in case you do not know anybody, please read the book Alice in Wonderland by Lewis Carroll. Or you can read also the Sukumar Ray's Hojoboro Law. They are about the same. Let me read it. There is a place like no place on earth, a land full of wonder, mystery, and danger. Let me read it again. Just listen very carefully. There is a place like no place on earth, a land full of wonder, mystery, and danger. If somebody asks me, talk about nanofield, I cannot do anything better than this. This is surprising that a novelist talked about something very close to science. And to give you some example, sorry, I'll be talking something sometimes in Bangla. I'll translate it right away for the benefit of other people. It is like, if you remember Sukumara's big famous poem, এক ছিল বিড়াল আর ছিল সজারু ব্যাকরণ জানি না হয়ে গেল হাঁসজারু কেমন তা জানি না. There is a duck, there's a porcupine. Don't ask me how, but they became a docupine. So this is the type of thing happens in nano world. That defies common sense. Or another example, basically it means there is a handkerchief or hanky, it become a Cheshire cat with a misty smile. You'll see something like that in nano world. It's hard to believe what we've been taught all these things, then they are not necessarily true anymore. Now, to give you the example of nano world, I'll have to go back to Richard Feynman. He was a visionary. He was a very colorful person. He has lots of things about nanomaterial, but what he said is almost prophetic. There is plenty of room at the bottom. There is plenty of room at the bottom. That means there is a lot of opportunities at the nano level. And for all of us, not one or two people. And we'll talk about it more. Just let me talk a little bit about this colorful person, Feynman. One of the famous quotation is that the first principle is that you must not fool yourself. And you are the easiest person to fool. So believe the data. Don't try to convince yourself because of based on your past experience, this is the way the life has to be. No. Another thing is very important, I am going to quote again. If you thought that science was certain, well, that is just an error on your part. We'll talk about it more. Before I go further, let's talk about what is nano, what is billion. And you know, in nanometer, right? A typical person is about 1.6 to 1.8 nanometer. If you stretch your hand a little bit, then you'll get a nanometer, a meter, 1 meter. Now take that meter, divide into 1,000 pieces. What you get? All engineers know it's a millimeter. It's almost like a pinch of your finger. Now take that millimeter, divide again into 1,000 pieces. You get a micron. Okay? It makes sense. Micron is 10 to the minus 6 or millionth of a meter. What does it really mean, really? Just touch your hair, feel it. You know how much it is? 150 micron, about. Human eye cannot see anything smaller than 10 micron. That is micron. Now take that micron, divide into 1,000 pieces. You'll get a nanometer. Let's take a step back. A billionth of a meter is a nanometer. Split your hair into 1,000 pieces is a nanometer. Talk about splitting the hair. আমরা যাকে চুল ছেঁড়া বিশ্লেষণ বলি. Splitting the hair, that is a nanometer. We cannot see. Give you another example to understand what is a nanometer. Think of Earth, the whole Earth. If we divide into a billion pieces, the smallest piece will be a soccer ball. Think about it. Whole Earth, billionth of a piece will be a soccer ball. Take the soccer ball, make another billionth piece, you will get so-called buckyball, which is a classic example of nanoscale material. Another we can think of India. How many people are there? About 1.3 billion people. Now you are one of them. You can think yourself as a nanometer representation. You may say, Kamalda, what you're talking, that doesn't make sense. Yes and no. Yes, there are a lot of differences between all the billion people in India and yourself, but look closely. There are some similarities. Chemically, you are the same. You have the same type of physical features. You are definitely different from a person from Africa or West Europe. There are some similarities, dissimilarities. So sometimes your similarity, your characteristic behaves, aligns with other Indians, sometimes there is not. This is exactly the nanoscale. That is why you need to make sure you believe in data, not your intuition. This is our famous nano celebrities. Now everybody knows about COVID. Their size is about 80 to 100 nanometer. Then people are talking about solution. Then another thing, you know it for sure, is your mask. If N95 mask is about, make sure the 95% of the 300 nanometer particles can be stopped. That's what it is. Now you understand, if nothing, the power of nanometer, at least from your experience with COVID. Now you may ask, okay, so what? I understand it's a very small thing. You may ask me, it's a very, very small thing, but what's the big deal about it? If I can make something in the nanoscale, what's the big deal? Can I sell it? Can I make money on it? Can I do anything? Can I make an impact with the human? Of course you can. If COVID can, you can do it too. The question is how and why. First example is advantage of nanometer, or what is, we are trying to say scaling matters, scale matters. This is a slide I want to, my students to look into very closely, because this is the slide I can spend another hour on. This is the most important slide in the whole presentation. because this is where the importance of nanometer comes into play. The first important thing is because it becomes larger surface area. Think of a, say, 1 centimeter cube. Now take the same cube, divide into nanoscale, you'll get millions times surface area. You may ask, Kamal, what's the big deal about it? Here's the example. Think of a sugar crystal. Amra jake michli boli. Take a sugar crystal and dump it in a beaker, in a water. How long will it take to melt? Maybe days. Take the same sugar cube, crystal rather, then make it a very, very fine sugar particles. Take the same thing, dump into the beaker, it will almost minute or two, it will dissolve. See, chemically I didn't change anything, nothing was changed. It's the only thing I did, increase the surface area. It made a huge difference. There is always some doubt, or then they may say, so what? Here's the so what part. There are a lot of chemical reaction depends on surface area. They'll be very powerful there. With the same mass, with increased surface area, you can activate that reaction very fast. Here is a classic example. Most of the drugs we use are what we call hydrophobic and correspondingly lipophilic. What it means, phobic means they hate. Hydrophobic means they hate water. These drugs hate water. On the other hand, they love lipid, that means oil. So what happens, because the drugs are mostly sparingly or mostly insoluble in water, they have to be dissolved into oil or some sort of lipid, then inject into human body so that they can administer. What does it mean? Take an example of, say, Taxol, a drug for cancer. And what they do, they mix it with alcohol and castor oil and then inject to the body. Now think of drinking literally every day 10, 20 centimeters, cc's of oil every day. You start throwing up. But we are forcing it through injection, so what happens? Body doesn't like it. We lose all our hairs, we feel nauseating, everything, etc. Now go back. Using the surface area criteria, if we can make it soluble in water, it's literally a nice drink. There's no side reaction. This is just a simple example. There are many more like that, this surface area. Now let's go to the other thing, another area, near theoretical behavior. If you look back as a mechanical engineer or a material scientist, you know that the material behavior depends on purity of the material. Typically, all the materials have defect inside the body. Typically, they are 10 micron in size. Now, if I tell you that I can make a nylon string that is about as strong as steel, probably you will be thinking, Kamal, are you smoking something? How can you make a nylon string as strong as steel? The answer is yes, I can, at the nano scale. Why? Because most of the defects is about 10 micron, and the defects, what it does, introduce so-called stress concentration. So what happens, even if we're applying, say, certain amount of stress, in reality, inside the system is saying 4 to 10 times higher stress. And there are many of them. So what happens, the actual strength comes down very low. The real strength of a material should be the force you need to separate two molecules in an ideal sense. That exactly happens with the nanoscale. Because the material itself is now nano level, there's no opportunity for defect to exist in the micron scale. That's why we can do the theoretical strength are so close. And at that, the Young's modulus and the strength is about the same order of magnitude. But bottom line is that at nanoscale, we get significantly higher strength. And if we can do it, we can take advantage of it. Then another thing I can talk about, physical properties. Now, if I tell you that the melting point of aluminum is what? About 700 degrees C? What was the melting point of steel? Depending upon the composition, maybe around 1200. Glass is about 1400. Now, if I say, no, that is not true. What I've been told by your school teacher or the college professor is not necessarily true. I can melt glass at 700 degrees C. You may say, oh man, here he goes again, talking bakwas. He's just making nonsense. No, it's not true. I have shown in my lab, depending upon the size of the particle, glass particle, it drops down from 1400 degree to 700 degree, and of course anything in between. I have not published it, but I have seen it. And the reason why I didn't publish it, that is another area for another day. Basically, I want to make a patent out of it and monetize it. This is another opportunity. If we work on the nanomaterials area, there are a lot of opportunities, new discoveries, new applications, and you can monetize it. That's the reason I didn't do it. We'll talk about it later. Then another example could be optical. If I say, what is the color of gold? Everybody will say, oh, okay, of course. What is that? That's not even a question. You're all right. I may smile like the Cheshire cat. No, it could be blue or green. You may say, oh, here you go again, Kamal. No, I'm not wrong. I'm not bluffing you. It is true. Depend on the size of the glass or rather gold nanoparticle. It could be blue or green. Take a step back. Why it can happen? Why you get color? Because light reflects from it. What is the wavelength of typical light, visible light? Around 140 micron or so. Now, if your particle is surface couple of nanometer, the whole light cannot reflect. So depending upon what the size, their color changes. So these are the things in a lot of stuff. Another thing is that different physical properties. As I told you earlier, same material, depending upon the size, your physical characteristic changes. It could be mechanical, it could be optical, it could be solubility, it could be anything. So these are the reasons why we are interested in nanomaterial. The biggest challenge is that there are so many types of material, hundreds of thousands of material, and each material will have different types of material properties. So what is happening, and people don't know it. They're exploring right now. Why they don't know it? There's a reason for it too. Because it is very difficult to make nanomaterial. They're not sold in pounds or tons. They're sold in grams. They're very expensive. And now, even if we're ready to, let's assume, if you are ready to spend the money for a specific application, even if we ask for, I want, say, 10 kg of gold, they cannot give it. It's not the money anymore. They cannot simply produce it. So between the high cost and low volume, the work on nanometers is very limited. That's why hundreds of thousands of people working on nanometer, trying to find a new application, new idea, and then talk about it. Right at this moment, hundreds of thousands of people are working on nanomaterial. We'll talk about it a little later. Here's some timeline. You'll be surprised that first nanomaterial was devised more than 100 years back in 1902. But at that time, which is Morton and Cooley, then Formals did it in 1939. They call it fine fiber because they didn't know that they are making nanofiber. Then came Feynman. His famous quotation, there is plenty of room at the bottom, 1960. I'll jump into 2010 because I didn't realize it before I started talking about it. And then I suddenly realized, oh my God, what a serendipity. Our first spinning was done exactly 50 years later, 2010. In between, in 1965, first the stereo scan or the first ACM picture came into play, and first micrograph of fine nanofiber of 1980. And my good friend, Joyce Dorsey, who lives in Tennessee, Chattanooga, Tennessee, he first introduced electrospinning. Basically, electrospinning is nothing but Formal's 1939 fine fiber. But he rebranded it and he popularized it, and he started the whole revolution about nanotechnology. He's the first person to introduce nanomaterials and its powerful applications. And of course, we started talking about 2010. First, another disclaimer here is that nanomaterial, as you understand, is a huge field. I know nothing about it. So I am focusing on my research experience, and whatever I've done, my focus is like that. And now we can multiply it 1,000 times and see how huge is the field. This is an interesting picture, again from Alice in Wonderland. Basically, I'm trying to say, as I told you earlier, there are a lot of excitement, a lot of amazement, a lot of challenges going around on nanofield. This is just a glimpse of it. If you look at the picture, very interesting, right? But look closely. Let me expand it. See? Can you see it? Fact and fiction and mixing up. This is nano world. I cannot say anything more than that. So basically, I can say the famous quote of our Rabindranath Tagore. We can talk about it. And what is the famous quote of Rabindranath Tagore is that Anando Dhara Bohiche Bhuvani. The world is in a festive mood because everybody is excited about nanomaterial. They are doing anything. Every day we are finding something. We'll give some data right away, then you'll understand what I'm talking about. But before I jump into the nano world, let me make sure one thing. There is some warning sign. Because of the low volume and high cost and unknown behavior, you cannot just walk in. As Feynman said, nothing is fixed in science. You have to understand it. You have to look at the data closely and then believe the data. If it means you have to throw a sum per concept, so be it. Melting temperature of materials is not fixed. It depends on size. There is a size effect. You can significantly get different material properties at the nanoscale. So this is very important. You are more than welcome in the nano world, but make sure that you believe the data, not your intuition. Your intuition will fail many, many times, and I have seen it again and again. Now I'll talk about, as I told you, Anandodhara Bohiche Bhuvane. Lots of world festive going on. At this point of time, hundreds of thousands of people working on nanomaterial. I'll give you these slides. I'll go through a little fast just to show you that how different areas in nanomaterials is being explored and how the excitement or the applications of nanomaterials is increasing exponentially over the last 1995 to say about 30 years, when my friend Joyce Doshi started the electrospinning process. Now, these are the typical areas of research people are doing it. I am holding a picture of a book. It says Industrial Applications of Nanomaterials. We are talking about that. They are typical applications. This is just a pie chart showing materials area, pharmaceutical area, aerospace, electronics, chemical manufacturing, other. There are a lot more than that. I'm just quickly going through the content of this book. Surface coating, then sports, aerospace application, automotive industry, military, food industry, water treatment, construction industry, catalysis, nanoelectronics. Let's go into it. There are now, as I told, there are books written on it. So bottom line is that independent of your research area, independent of your interest, you can take advantage of nanomaterials in any of these areas, whatever interests you. Here is a market analysis. Look at these numbers. Don't focus on specific number. Look at the trend. Bottom line is that starting from about, actually it was a lot less than few $1 billion initially in around 2000. Now in 2020, the projected market size is $500 billion. Take a step back. Trillion. Mind was boggling with billion. Now we are talking trillion. That means if this is a number you can think about it, every person in India will get $1,000. Every person. That's a trillion. And this is the impact of nanomaterials, which literally 30 years back did not exist. Can we think of another application, another area? Very difficult to think. There are areas. I'll have to accept it. But think about this. This is an opportunity. Another thing, look at the publications. 2000, it was about less than 100. Now 2019, we are talking about 1,600 publications. It's exponentially growing. Again, don't look at the numbers, absolute number. Look at the trend. That means everybody is jumping in. It's a gold rush. Everybody is thinking. This is a total number of patents. Again, look at the numbers. Look at the trends. Don't focus on specific number. Now, couple of hundreds to more than 1,000. Guess what? I myself have half a dozen patents in this area. And I'm nothing. Multiply these thousands of people. There are a lot of opportunities. And I can tell you, to make a patent, you don't need to be a genius. All you have to be, as Thomas Edison said, 90% perspiration. You have to sweat a lot. Now, what's the role of different geographic location? How they are doing? As expected, like every other field, mostly, US is controlling 30% of the research. Then comes Japan, then Europe, Asia 11%. Again, look at the big picture. Don't get hung up with smaller numbers. This is just another example, health-related patent. If the top 7 countries control 88%, actually I was looking at the number more closely, top 10 countries controls more than 98% of the patent activities in this specific area. Good and bad thing is that India has got half a percent. So bad, of course, because when China is 20%, we are half a percent. That means we are talking about less than 100. It's a very small number. But at the same time, good thing is that at least we are in the game. In New York City, they make a beautiful advertisement. I love it. They say, to win the lottery, you have to be in it. So at least we are in it. By the way, as a sidekick, let me tell you, in case you did not hear it, there's a saying in this country, we call it, lottery is a poor man's tax. So don't buy a lottery ticket. I never buy. Now let's jump into action. Okay, you may say, Kamal, you convinced us, this is a very interesting area, I want to get in. But how I get into it? So basically you start with nanomaterials. Who will give you nanomaterials? Nobody. But they're expensive. They're very little available. And if they're already in it, they want to use it for themselves. They don't want to share it. How we do it then? Do it yourself. Then how we make nanomaterial? There are two approaches. What we call bottom-up and top-down. Bottom-up is mostly scientific approach. They try to basically assemble molecule by molecule and they try to make that one. I am an engineer. I start other round. Even if the scientific approach is very pure, very focused, engineering approach is not pure, but that serves my purpose. That's all I care. Okay? What you do in this approach, start with the bulk material and keep hammering. Make as small as possible, and then you get a mix of nano and micro, and depending upon quality you need, you may have to separate them or keep it, whatever you want to do it. But good thing is that it's a high yield and the price is acceptable. Unlike the scientific approach, with the purity, you pay high price. But engineering approach is not easy. As we say in this country, common sense is not very common. It's easy to say, but it's very difficult. Now let's try about top-down approach. Electrospinning, port spinning is technology. I will talk about that. As I told you, this is my journey. There are different ways of getting there, but I specifically look this one because that's my area of interest. We start with this electrospinning. As I told you, my good friend Joyce Dorsey, he did it as a part of his PhD dissertation. The concept is relatively simple. Take a syringe and fill it up with dielectric material. So dielectric material, by definition, is a non-conductive, but all the surface charges is on the surface, whatever if you put an electric field. So once you have that one, take a dielectric fluid and push it through a nozzle, drop by drop, and now subject the drop in a high voltage power, like 20,000-30,000 volt. What is happening is that, imagine as a mechanical engineer or material scientist, that there is a drop of water or fluid which is charged and it is subject to a huge force of attraction. So it will try to split it and then go for it. I can go step by step. I can show you how millimeter size nozzle lends itself to nanometer size fiber by reducing this fluid into 3 orders of magnitude. And this is what I get. So let's take a step back again. So what we are doing here? What we are doing, a dielectric fluid and high electric field, try to split it. Then we get this one. If you look a little closer, this is what you get. This is called Taylor cone, what you see in the center. This is a Taylor cone. Actually, Sir Taylor, he came up with this concept. That's why it is under his name. Think about this. When the rain drops, what is the shape of the rain? Tear shape. Why? Because of the huge electric field it undergoes from cloud to the earth. That's why it never have any other shape. Because of that, it's a water is a dielectric material. And that's why. Now, what is happening in this technology? We are getting very high quality nano polymer fibers. But limitation is that your material has to be non-conductive material. Otherwise, it will not work. Elective. You cannot do the same thing with a conductive material like a metal, because it will be like your electric lightning rod. It will simply switch back. No splitting. So I did some research on that area. On the left-hand side is a research. There is an experimental result from the MIT. I simulated the whole thing in my computer, and actually I didn't do it. My student did it. Okay, and this is what I get. See, look at the similarities between the two. Basically, all it says that how you can control the parameters in an electrospinning process to get different types of nanofiber. How they're controlled, it depends on electric field, nozzle size, distance between the nozzle and the electric plate, fluid materials, viscosity, and all the good stuff. And I could reproduce it. And you realize that this picture on the left side is very highly magnified. We are talking about nano and micron. What you are seeing on the left side in the experimental picture is the leftmost end. This is all you can see. That means it has to be at least 10 micron. It goes beyond that to be a nano. So there is a couple of companies, they started the same process. They call it nanospider. Basically, instead of using one nozzle, there is multiple nozzles. They started to make nanofibers. And they are somewhat successful because they could do 15, 20 nozzles together. So they could improve the productivity by 15, 20 times. But still, unfortunately, their productivity is less than a gram per hour. Let me repeat. The productivity of electrospinning process is a couple of grams per hour. For industrial application, that is next to nothing. So, when I started...
Kamal, just wanted to mention that we are almost like for the slide deck halfway mark. There are 20 more slides to go. And the time is 7:53 here. And
Fantastic.
I just wanted to let the audience know, if you have any question, please feel free to type it in your chat box, which I will park it to Kamal according to his lecture. Thank you. Please continue.
Thank you, Biman. This is one problem with this topic. I always get carried away. Okay. But bottom line is that let me try to slide through faster. And thank you, Bimal, for warning me right in time. There's a major issues. So as a mechanical engineer, I thought, okay, if there's an issue, there's an opportunity. How can I get around it? If you look back, what I said, basically it's a pulling the fiber as fast as you can using some sort of electrical force. As a mechanical engineer, I thought, what the heck? I can do is the centrifugal force. What's the difference? Lo and behold, we got it. We called it force spinning method. In case you don't realize it, think about what you call Budir Matha Chul, the sugar candy, same damn thing. Actually, when I told first Joyce the same thing, I have a better way of doing it. He told Kamal, are you kidding? You're trying to sell a candy machine for $100,000? Okay, let's see. And that's exactly what I did. And by the way, this paper I wrote on force spinning, electrospinning to force spinning, it has got more than 400 citations. This is one of the top titles. Actually, it's a huge deal right now. People are trying to do it because one of the biggest thing advantage it has got is that it has got the productivity more than 1,000 times of electrospinning. Now we are talking real deal. Now you can make real applications. This is the machine for lab scale. They sell it for $1,000, $100,000. They sold a machine for like this for $1 million. Basic, same concept, cotton candy machine. Now, these are some of the pictures we got. And one of the biggest advantage of force spinning method is that it don't have to be dielectric material. It could be even a metal, conductive polymer, no problem, because it does not depend on electric field. Apart from safety, productivity improve. We remove many of the barriers of electrospinning method. So now it is one of the hottest field of research. People are talking about it. Mine to market. How did I make money? In 2007, we filed a provisional patent. Then 2008, Five-Year Technology Corporation, McAllen was formed. The university licensed the technology to this particular guy, Hillary. And then first patent on force spinning was finally issued. They realized the difference. 2007 is provisional patent. Actually, we found the patent after 5 years. Good thing is that in the patent method is that your space is reserved. Nobody can violate your patent. So that's why you could start the company in 2008. Then finally, 2014, we got 3 more patents. Then 2016, Clarkwood Corporation acquires our technology for $20 million. Then 2017, Parker Hannifin is a multi-billion-dollar company. They took the technology. Unfortunately, we don't know what the heck going on because they are everything under a closet. So far, so good for force spinning technology. Now, is the only way of making nanofiber? Absolutely not. You are a mechanical engineer. You are limited by imagination. So I moved away from fiber, metal. Then I started with glass, waste glasses. We developed a technology called ACE, automated, continuous, enclosed. There are a lot more details, of course, I'm not going there. But think about that. This is the solid waste. It has no value. It has no value. In this country, you can get it. This guy, crushed glass for a couple of cents, pennies a pound. Now this guy, you can sell it for $1.50 a pound. That means $3,000 top. Look at the scale, 2 micron. And this, one of the things I want to confirm or make sure you understand, since you cannot see anything more smaller than 10 micron, so you need a gadget to do it. That is called scanning electron microscope. You must have a scanning electron microscope at your disposal to do any research whatsoever. Otherwise, they are out of luck. This is again, these are 10 micron. This is the smallest thing we can see. And these are so-called scale bar. Now see all those things. Or this one, this is 2 micron. Remember your the whole thing is 2 micron. So that's what you need in ACM. Now again, what's the big deal? As I told you, there are a lot of interesting applications I found. It could be used as a flame retardant paint. It can be used as thermal insulation, it could be a transportation fluid, self-cleaning stockbook, cosmetics, dental, drug delivery system, environmental radiation, remediation sensor. Let me tell you one interesting application. From waste class, we are talking about cosmetics. I really made a cosmetic out of it. And of course, I tried to give it to one of my friend and colleague in the university. She didn't take it. She said, Kamal, I'm not going to take chances with your metal. Okay, you don't have to take it, but look at it. Finally, she agreed. She put it on her hand. It was a nice orange color. Yes, I can make it. Detail is to be discussed, but we can do it. This is some behavior we did it. What it did is, this is the regular paint. And what has happened is it charged in a 5 minutes time, and look at this, nothing happened. Again, there are details. This is another example. I use the same concrete, concrete, and mix it with glass nanoparticle, and put this plastic soldier, and put the whole flame. Even after 45 minutes, nothing happened. Regular concrete, it was melted. This is another interesting application. Frankly speaking, probably this is the first time I'm talking in a public place like that, because I love the college. I never this in open public. And I know it will go to YouTube. And I know people will jump in. These are a very interesting characteristic. These nanoparticles are hydrophobic and lipophilic. I put some oil and look at this. This glass nanoparticle absorbed it, became heavier and dropped down. So it absorbed oil. Anybody interested, you can talk to me. It's very, very fascinating application. Think of all the oil spill all over the world. We are talking about hundreds of millions of dollars, billions of dollars invested. It's possible. My challenge was that I don't have capacity to make tons of them. Now I have a way out. I'm talking to one of the largest recycler in US, strategic material. They are talking about it. We will talk about it. Now we are coming close to my presentation. Basically, all I'm trying to say, yes, it is an exciting world. It's a challenging world. It's an amazing world. It's an enchanting world. But to get into the action, you have to be careful. Don't get drowned like this guy in the avalanche. You have to have some common sense. You have to have some confidence in yourself. You must generate the data with lots of hard work, a lot of perspiration. Then only you will be successful. If you think you want to do research to make money, please don't come here. This is not for you. These are do's and don'ts for nano world. You have to be very meticulous. You have to be imaginative. Keep doing mental experiment. Learn new tools, both theoretical, experimental, and simulation. You have to know those things. What you don't do, don't assume anything. If you remember when I started the discussion, I told the melting point of metals are fixed. No, not in nano world. So don't assume anything. And just because you can come up with some ideas here and there, don't daydream and think that you can be quick rich. Remember, even our patent, it took 7 years to come from concept to reality. But it can happen. If your focus is on research, interest, excitement, be my guest. If you want to be quick rich, please do something else. travel light, travel right. What you need to do, you must have certain tools. You must have access to nanomaterials. If you don't have it, make it. If you don't have it, you cannot make it, talk to me. I can help you. I will not guarantee you anything. No. Okay? All I'm saying, I will help you. You must have a material characterization lab. So there must be some collaboration. Nano research, by definition, is interdisciplinary. Mechanical, material, civil, electrical, everybody has to cooperate, depending upon the interest. And last but not the least is tools of the trades, I3, interest, innovation, and investment of time. Coming back to the tool, ACM, scanning electron microscope, I want to talk a couple of them. You must have a working prototype. You cannot go to a war without your rifles and ammos. You cannot be so-called Nidiram Shardar. You have to have the tools. It doesn't matter how imaginative you are, it doesn't matter how hardworking you are. If you don't have the tools, you don't have the tools. So ACM is a must, and it must be working. And I have seen that one of the biggest things you need, really, the ACM, in case you do not know, by the way, ACM stands for scanning electron microscope. Basically, here the picture images are made using electrons, not ordinary light. So that's why you can go for very high resolution. But the challenge with the scanning electron microscope is that you must have a high vacuum. That means so-called sample preparation is a huge deal. It takes time, expertise. So what is available nowadays actually started about 1995 and later on. They call it environmental scanning electron microscope or environmental ACM. The advantage of environmental ACM is that you don't need any surface preparation. You can literally see the sample at atmospheric pressure. So you can take the sample, put it there, and you can see it is. I can have an ACM picture literally in half an hour with your environmental ACM. If you go for regular, it will take a couple of days. So that is one thing you need to have. Otherwise, you'll be very much handicapped. Without ACM, forget about it. You cannot do any nanomaterial research. And even if you have a ACM, better be make it environmental one, so that you can take the sample. You have to take hundreds of samples, thousands of pictures, and you need that kind of thing. So these are the something in it. What I talked about, I don't know how long, 45, 50 minutes. So let's summarize what it is, so that you remember what I said. Most important thing, there's plenty of room at the bottom. Everybody in the room can jump into it. Hundreds of thousands of people all around the world are working on this area. Size matters. As you go smaller and smaller, you get, like Alice in Wonderland, will have a lot of new things. You didn't know it. Keep faith on data, not an intuition. If you have some issue, maybe you made a mistake, you got a wrong data, possible. Repeat the experiment meticulously. Repeat experiment again. Get the data. In this country, we say, measure it twice, cut it once. Same thing here. Do the experiment as many times as you want, but make sure your data is correct. Once you have the data, forget our intuition. You got the data. All imagineers are welcome. Engineers are creative by nature because they solve problem. Problem exists, people live with that, but engineers walk in, they solve the problem. We are creative. We create new things. We make an impact. All you have to do, add another ingredient, keep dreaming. Be a dreamer. Think of something, you can make an impact to the society. You can get you can get excited. Knowing new things, people didn't know it. Don't try to be rich. Be significant, rather successful. There are a lot of success people, but they are for themselves. Be significant. So that other people say, oh my gosh, Kamalda made a difference. I'll be happy to know that. I don't care how much money you have got. I care. Like Amutavada. He has so many successful students. He made an impact. He's a visionary. I want people like that. Be an imaginary. Be a dreamer. Success will come on the way. Thank you very, very much for the time. I really appreciate it. Any question? It's an open forum now. Thank you.
Thank you very much, Kamalda. And the session is now open for Q&A. So you can unmute yourself, speak to the screen, or type your questions in the chat.
I have put my question in the chat.
Okay.
So Kamal,
Let's see.
wanted to know that how important it is to have a good background in quantum mechanics to do real good research in nanoscience. Because in India, I find a very large number of people, they are doing work in nanotechnology, but they are really mundane activity because they have no expertise in QM.
Good point. And let me make my disclaimer first. I have no background in quantum mechanics. Okay?
Is it important?
But, as I told, but the point is that what you said is absolutely right. It is like, it's a nano world. It's an interdisciplinary thing. There are a lot of areas you need to know, and you cannot know everything. So what you need to do, start what you know and go from there. You are absolutely right. As I told you in my presentation, there are two approaches to nanotechnology. One is bottom up and top down. Okay? Scientists prefer the way of bottom up.
Yeah.
So you do need that experience. And if you have, you are way ahead in the game. If you don't have, you are handicapped. Does it mean you cannot compete? No, you can still compete. So you are right. As a physicist or knowledge with quantum mechanics, you are definitely ahead in the game. But even engineers can jump in. At the end of the day, what do we want really? We want to make an impact. We want to make an application. So if you can make an application for the society, for the good of anybody, or if not for today's world, for tomorrow's world, you are more than welcome. Yes, I must say, if you have got a background of quantum mechanics, it will help a lot. But that is not the only way. As Ramakrishna Dev said, Jata Maut, Tata Path. There are so many ways to reach the target. Okay, quantum mechanics is one way, sure. I know nothing.
Okay, Kamalda, thank you. The next question comes from Shushmayan Trivedi, that in one of your earlier slides you mentioned we are nearing to theoretical grounds at nanoscale by avoiding scope of crystallographic defects. But at nanoscale, principle of continuum might not hold true. Will that not carry us away from theoretical grounds even more?
Can you repeat the question? Let me digest it. I didn't get it.
It's in the chat box. Essentially what he's asking, from your mention that you are nearing to theoretical grounds at nanoscale by avoiding crystallographic defects. But at nanoscale, principle of continuum might not hold true. Will that not carry us away from the theoretical grounds even more?
the way to look at it is that Mother Nature has her own ways. All we can do makes a series of assumptions. So what is happening is that we are still at the nano level. We are definitely far from molecular level or subatomic level. So our approach is that based on this assumption, we can only go this far, not further. Okay. So as Einstein said, I love the quotation. Any time I get a chance, I quote it. Make it as simple as possible, but not simpler. So if we go to at the nano level, we still are at the nano level, not the molecular level. So whatever the theoretical physics or subatomic particles or molecular theories, molecular dynamics says, they're still valid. We are one step away from there. Nano is
they are
not
doing
Armstrong. So they are different.
Molecular dynamics, I think they are using with high-speed computers. At least some of the problems can be handled.
Correct. Can be. But the question is that, this is what you call multi-scale problem. One hand, you are trying from the top down, other is bottom up. Okay? Now, where we meet is a different issue. The question is that you can start from anywhere. But as an engineer, my objective is very simple. At the end of the day, what you are giving me, I'm a customer. I'm willing to pay you money if you can solve my problem. Okay? Of course, we are not talking Einstein. That's a different issue. And his things also, we are making impact. It took 100 years. But we are talking about at this point of time, you can come up with any model and you can come up with any solution, but as long as I can afford it, as long as it affects my activity, as long as it affects my application, I'm a happy camper.
Are you also working on carbon?
Actually, I didn't work on the carbon, but some of my friends are working on it. But that's another area, carbon nanotube and the graphite stuff. Oh no, I'm not there. I'm not working there. No, I am not. But I'm familiar with the field. Buckyball, yes, I am familiar with. They have got a lot of interesting applications, yes, but unfortunately not. All my
Dr. Biman.
Yeah.
Yeah, Biman, may I
Yeah,
interject? I want to say something. Here we
sure,
have
go ahead.
heard, yes, thank you. Here we have heard an original discoverer, an original researcher. This is a pleasure. For me, it was a pleasure to hear the Professor Kamal Sarkar. He talked from his heart. He was not reading anything. He knows the subject by heart. That is absolutely a delightful lecture to hear. So I am glad that I attended this lecture. But I want to add a little bit of my input in it. In cancer, the medicine could not reach the cancerous mass. So what they go on doing, they went on reducing the medicine particle size. And ultimately, when they reached nanoparticle size for the medicine reached the cancerous cells and it started to work upon. This is one area, I mean, it kept me very interesting. The approach, the human approach for nanoparticles. Well, again, Professor Kamal, thank you very much. And I am glad that I attended this lecture.
Thank you very much, Achyuta.
You made my day. Okay. And please call me Kamal. I'm a
Okay,
chota
Kamal.
fella. I'm a very small Russ.
Okay, Biman, I'll add one more thing. As Professor Amitabo was telling regarding quantum mechanics, one funny thing happened with Richard Feynman. His doctorate students were leaving him and going to some other professor instead. So people started jittering him. What happened? Your students are leaving you. What is the problem? Then Feynman said, look, they wanted to understand what is quantum mechanics. That's the problem. So this is the problem with quantum mechanics, Amitabh.
Achyuta, let me tell you one thing. So along the line, what you talked about the cancer thing. Actually, this is one of the reasons. What we are doing is that these nanomaterials, there are two areas of research right now. One is the medication itself, what we call drug delivery system. Other is diagnostic. How to identify the cancerous cell. So there are two different disciplines. One is diagnostic to identify the cancerous cells. Other is your treatment itself, drug delivery system. You'll be surprised to know that I don't know what happened to the research about 20 years back. One of our, again, Bengali fellow, physicist, I forgot the name exactly, but he saw something in Indian Railway, and that one guy was selling balloon that carried balloon within a balloon. And he got the idea. And he applied to NSF and got the multi-million-dollar contract. And what he did, his outside balloon was nothing but diagnostic thing. He was trying to identify where's the cancerous cell. And once it goes there, it attaches itself to the ground. That was his proposal. And then once it attaches, it bursts. And the inside cell gives you the drug. That was his concept.
Great.
And yes, you are right. There are a lot of research going on.
Yeah,
But all at the nanoscale. Sorry, Biman.
No, I see a comment from Animesh Talapatra, not a question. Basically, he's doing his PhD on nanomaterials using lamps and Material Studio, and posed the challenge that experimental works are very expensive. He's using graphene nanomaterials. Yes, many a case experimental works are expensive. You need sometimes very sophisticated tools. As the scale of resolution decreases, so the cost of the equipment increases. It's very, very common understanding. So yes, we have to overcome them challenge, and then like with the advent of many different computational techniques, especially like processing big data and all that, the projections are also getting enhanced. So yes, I'm sure the challenge is there, but at the same time, enormous work is being conducted to overcome the challenge in that same direction. So
since I'm out of the country, I cannot tell exactly. But actually, I left India in 1978, so I'm way out. I'm totally out of touch. I do not know, but I can tell you one thing here is that SCM is the basic tool you need, and in every university there are multiple of them. Literally, so in most of the universities, I got at least a dozen or so. But I do not know the status in India. So I do not know. I'm expecting any institute of higher education will have multiple SAM. And that's a basic tool. But you are right.
In our Bengal Engineering College, there is a separate nano lab, and they are doing work on nanomaterials lab. They are doing work on nanomaterials. That much I know. Materials lab.
Yes, Uchida, just one quick thing. Yes, since we are talking about characterization facility, I have some familiarity. I was in the faculty of BE College for a long time. In my time, like back in the 90s, we had ACMs, like as Kamala mentioned, that the resolution of an ACM, say about 10 nanometer scale, right? And when you talk about TEM, the resolution increases to about 1,000 times of that, right?
Correct.
Unfortunately, at BE College, if there is any current faculty from the materials background, they can say. But to my knowledge, the last SCM annual service contract was not renewed, and probably it is overdue for more than 9 months. And the TEM facilities is also down. We had a very sophisticated TEM, but the TEM is not running. So there are other things associated with that. That's the local level problem, not a platform for this centenary lecture. But the key point is, like, not only having sophisticated equipment, you have to have the right kind of maintenance contract and upkeeping those equipment, researchers actually utilizing those equipment, and essentially allowing graduate students to use the ACM. Just as an example, like when I came to Michigan State for my graduate work, I was working on like characterization of dislocations in ordered intermetallics while we are doing in situ staining in the microscope. It's not my lecture, it's Kamal's lecture. I do not want to add any further. But key point is whether I am independently able to use the TEM or not. My major professor or advisor came to me, took the microscope totally out of alignment, and gave me only 20 minutes to succeed. If I could bring it in alignment, then I'll be allowed to work independently in the lab. If not, then I will not. And that's the kind of challenge posed to the graduate students and also the offer given to them. So, but when I could do it within the stipulated time, that gives me the confidence that, yes, I own the microscope. So that kind of mentality needs to be encouraging or inspiring. So there are challenges. Of course, we are moving in the right direction, but probably we have to move with a little more rigor and intensity. That's my only comment to this gathering.
Iman, you have touched a very soft point in our mind, in all our minds. All the people who are listening, who love our institutions. It is so sorry thing to see the institution is going to drugs. I'm sorry to make a comment in a public forum like this, but it is from pain, my mental pain.
No, I'm just saying, Uchudha, just we need to be equipped with everything. And another thing Kamal mentioned about the child, I cannot just refrain myself from that comment, especially for the students who are here in this forum. We are talking 2022, right? So you have 35, 40 plus years of professional career ahead of you. But be assured that the job that is coming in the 2030s, 70-80% of them are not defined yet. So essentially, you prepare yourselves with the adequate amount of toolkits and whatever you can gather. And this is, you are a student right now. This is the time, we call it in a cliche sense, that drinking from the fire hose. One thing I cannot I do not even attempt to translate that. Those who can understand Bengali can understand, according to Kobi Guru, Jiboner dhon kichui jay na fela. So whatever you are gathering at this point in life is going to stay for you for the next 40, 45 years of professional career. So gather as much information to as much depth as possible. And then find out your own niche area, which you will be carrying out for the rest of your career. Look at Kamal. He graduated with a mechanical engineering background, worked for like a space research organization, did his master's from a metallurgy focused program, worked in biomedical devices. Then he actually went on to improving the characteristics of the plasticizers. That actually goes in the drug delivery mode for delivering cancer drugs. And he was one of the pioneers in developing those non-DHP products for the drug delivery tubings. Okay, so that's the kind of work. And look at him right now. He's force spinning, right? Producing nanomaterial, trying to understand what the influence of increasing surface areas and surface characteristics bring to the fundamental nature of the physical characteristics of the material. So essentially, knowledge truly has no boundary. But gather as much as you can from your faculty members, from other open sources. In our time, that was not there. We have to go to the library, drop our identity card and go there. And if the photo is misplaced or you cannot be identified, you will be barred from entering the library. So gone are the days. You have all the resources at your disposal, but try to use it in a judicious manner. That's going to pave the path for your professional journey.
Thank you, Biman, for calling me.
Kamal, I just want to thank Biman. Biman has done his job as a coordinator beautifully. The last statement, Biman, you made, how can you drive this in the students? That is a man, we are just using 5% or 6% of our brain. Kamal shows that what human mind can achieve. What if you try, if you just try, what human mind can achieve. So again, to both Kamal and Biman, I pay my tribute from my heart. I being 81 years old, and I love my institution, and I love the students who I hope has listened to this and will take out something for them. Thank you very
না,
much.
thank
I
you.
will not
It's
talk.
অচ্যুতদা, thank you, অচ্যুত, আপনি ঠিকই বলেছেন। Without Biman, I could not been here.
No,
I
no.
am really thankful. I'm
Don't
really
say that.
thankful.
So we are approaching to the end of the mark. This is coming like 8:30 at my time. I have to work my day job now. But if there is any other relevant point with respect to Kamal's presentation, his email is right there on the screen. You can have a screenshot for his email. Also, like I want to thank Professor Sudip Ghosh and Dr. Bidyut Pal for giving me this opportunity to be here among these famous academicians like Amita Oda, Ashokda et al. This is my great honor to be here with all of you. So if there is no further question, I would like to thank Kamalda and everybody in the audience who made this lecture possible, irrespective of their commitments from their day job. So
Just
thank you
last
very,
word.
very much.
Can you
I give it back to Sudip and Bidyut.
Yes,
Kamalda,
I have a responsibility here.
Okay.
Oh,
I would
Shantanu is
request-
trying to say something.
Just
Professor
one minute only.
Shantanu
Kamalda's
Sarkar,
first
please.
lecture I have listened, the excellent one, and concluding also, Achyudat says that Vivanda's conclusion also equally excellent.
Yeah,
What is the
his
wrong?
piece of advice
This is first
also.
lecture also. Okay. The advice also. This is a very great lecture I have listened. Kamalda, this is Shantanu Karmakar. Okay, you have introduced.
Thank you.
Well,
Thank you, everybody, once again.
And on behalf of the department and on behalf of the Centenary Celebration Committee, I must thank the speaker, Professor Kamal Sarkar. I must also thank our session chair, Bimanda, and I would request Bimanda to virtually hand over the certificate of appreciation to our honored guest, our honored speaker, and also a memento as a token of appreciation for that. So thank you,
Oh, Kamalda,
Bimanda, for
it's my
leading the
privilege
session.
and honor to hand you over our digital memento. And I'm
Yes,
sure
yes.
when
Our
situation
digital and
normalizes,
yes.
you will
And the
visit
mementos
our
will be
parent
keeping
department,
here.
our mechanical engineering program at the campus and meet with all
Yes.
these folks. Thank you.
Thank you.
Well, thank you. In fact, it's I was just following the conversation, and it's really nice discussion we
We'll
had.
meet at your place, maybe in month of July or August. I'll try to meet you.
Is there some echo is coming?
Kamal,
আমি শুনতে পেলাম না।
না, Kamal,
অমিতাভ
yeah,
অমিতাভ কি বললেন? শুনতে পাইনি অমিতাভদা।
able to come to Austin. It is too much of echo I find in the sound. So I think I hope to
It's
meet you
breaking out.
if I can go.
বিমান, can you hear? It's breaking up. অমিতাভদা কি বলছে?
অস্টিনে যেতে পারেন না বললো, এটা বললেন অগাস্ট মাসে যেতে পারেন in the month of August.
Oh, can you hear me now? So I was telling Kamal that wonderful listening to you, and I hope that if I can go to Austin in summer, I'll definitely try to visit you. Okay.
Sure, that will be an honor for Kamalda. Thank you. Well, thanks everybody. Professor Ghosh, Sudip Ghosh, and Dr. Bidyut Pal. As I said, it was my great pleasure, and let's draw the curtain to the session. Thank you.